Hello, everyone, and welcome to today's webinar, Extremely Dose-Efficient EELS Spectrum Image Acquisition with Gatan eaSI Technology. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speaker at the end of the presentation. If we don't get to your question, we will follow up via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Dr. Liam Spillane has been working in the field of electron microscopy for the past 17 years. He started his career as a PhD student at Imperial College London, studying oxide-thin films using aberration-corrected STEM and monochromated EELS. After completing his PhD, he worked as a postdoctoral research assistant in advanced electron microscopy, working on the structural and chemical characterization of materials across a number of projects, including nanoparticle toxicology, ferroelectrics, nanoparticle catalysts, and solid oxide fuel cells. After leaving Imperial College in 2012, Dr. Spillane joined Gatan, initially working with the UK Sales and Service Group for a number of years. He relocated to Gatan, USA in Pleasanton, California in 2018, where he's currently the application scientist for Gatan's STEM-EELS and GIF products. Now over to Liam.
Thanks, Jonathan, and thanks everyone for signing in and attending the webinar. So we'll get started. So just brief overview, we're going to cover some detector technology aspects, things about the camera, then some things about the filter, and then kind of switch into a case study about a nice sample that we've been getting some data from recently. So detector technology, strictly relating to counting cameras. So we have essentially two types of counting detector technology. So we have what's called a counting monolithic direct detector or a thresholding hybrid pixel direct detector. So I've included both here just to kind of give some context of the hybrid pixel, because it kind of really needs some sort of comparison. So we'll start with the monolithic direct detector. So here we have active counting kind of in the pixels. So we have a thin transmission sensor. So essentially the beam goes through our sensor, and the sensor has small pixels. So in this case, 5 micron pixels. So this is kind of the technology that would be like a K2 or a K3 type counting camera. So large number of small pixels, transmission, kind of thin sensor. So if we switch over to the hybrid pixel direct detector or the thresholding counting, the geometry here is very, very different. So we have a thick diode layer. And what happens is the primary electrons will come and interact with our diode and completely stop. So they deposit all of the energy in that silicon type diode, form electron hole pairs. The silicon diode is bump bonded to this ASIC chip, and this is where the counting is happening. So the readout is happening in the ASIC chip. So geometry, as I said, is very, very different. So instead of having a thin transmission sensor, we have a thick diode layer. And then that's attached or bump bonded to our pixel array, so it's a large pixels. So instead of like 5 microns, like we have with the MAPS camera on the left, we're looking at kind of 55 to 150 micron size pixels in the thresholding detector. So quite different. So what's the specific system that we're working with? Okay, so we're working with the Stela camera. So this is a Gatan solution that's based around the DECTRIS Stela sensor. So it's utilizing DECTRIS hybrid pixel technology. And that is fitted to our continuum spectrometer. So we have two kind of variants. We can have a K3 based system with the Stela. So that's continuum K3 with Stela. Or it can be paired with the standard kind of indirect detector. So that would be continuum HR with Stela. So always two cameras, either two counting cameras or a standard camera plus the Stela. So how about eels? Okay, so eels with the Stela camera, we have exposed two spectroscopy modes. So we have a standard 32-bit high count rate mode. So if you look at the software screenshots later, you'll see that labeled as HQ. There's also a higher speed mode, which is labeled HS plus. So the speed increase when we're using that high speed mode is gained by doing sub-area readout, so half ROI, and decreasing the counting bit depth to 8-bit from 32-bit. So the trade-off for having this much higher frame rate, so for example at 8,000 spectra per second, is reduced dynamic range because of the lower bit depth in the counting. That really is never an issue for core loss, but occasionally we're going to overrun the counter for low loss. Okay, so that's a nice segue into kind of dynamic range. So we'll move on to the next slide. So dynamic range and the benefit of a fast shutter. So hybrid pixel detectors have a super high dynamic range. So we've got two kind of aspects that are going on. So we have linearity saturation at the sensor. We can take two picoamps per pixel, like per read. So we have like this really high kind of linearity dynamic range. And then we have what's called counter accumulation or digital saturation. So we can overrun the counting like digitally kind of after the sensor. So as I've already said, we have kind of 32-bit in one mode or 8-bit in the other mode. So yeah, so very high dynamic range, but it's not unlimited, okay? So this video we're looking at here is a live spectrum, live zero loss peak in vacuum at 180 picoamp probe current. And this is in the HQ mode of the camera, so the higher dynamic range mode. And what we're showing here is the effect of changing the view time. Okay, so the initial view time in the video was 100 microseconds. And then we're switching to 200 microseconds. Okay, so it's quite a lot going on there. So you can basically see that at 100 microseconds, we're not getting saturation. And then when we go to 200 microseconds, we get this linearity saturation. So you get this like flickering pixels. That's what's going on there. Okay, so one thing that we could do is decrease the probe current. Okay, that would decrease the intensity at the camera and get around this problem. For many samples, we don't really want to decrease the probe current. So if we wanted to do something like EELS and EDS together, we might need to maintain a high probe current to have good EDS signal. If our sample's radiation hard, like a metal or maybe a semiconductor, for example, we're just going to end up having to have an overall longer exposure time. So we might want to retain our high probe current, especially if we were doing dual EELS, we might want high probe current for our high loss spectrum. Now, fortunately, it's very easy to kind of work with this in the continuum. There's an electrostatic shutter, which gives us 100 nanosecond kind of shutter time or shutter pulses. So if we compare 100 nanoseconds to the camera frame rates, which are either 200 microseconds or 100 microseconds, we can get near 100% beam attenuation at those frame rates. So this is giving us a really extremely flexible way of controlling the probe current just in our experiment without having to do anything electron optical on the microscope. So what we can do is essentially only change the probe current if it's required by the specimen, not for some instrumentation reason like limitation by the camera. Okay, so dynamic range. So what next? Okay, high dynamic range, but we do need to use a shutter in most cases, nonetheless, for EELS specifically. Point spread. So the point spread function of the detector, okay, so it's fantastic at low kV. So below around 100 kV, we're probably going to expect to be able to get a single channel full width half maximum on a cold feg at say 300 millieV per channel dispersion. So what that means is our 1,000 detector pixels are really actually 1,000 useful EELS pixels, which is very strong. Radiation tolerant at low kV. We have low coincidence loss due to in-pixel counting. Large pixels, I mean, large pixels as a kind of a independent statistic is not really a bad thing. What really is constraining us is those large pixels need to fit in like a finite space. So it just reduces the number that we have available. So we're kind of going to end up with perhaps coarser spectral sampling than we would have if we have more pixels in the same space. Okay, so that's just some theory. We have a nice zero loss peak here that was taken at 80 kV. So we've got 0.36 EV energy resolution, probably at like 0.3 EV dispersion, or one higher, like 0.15. Let's look at some data. So this was some dual EELS data that was acquired from molybdenum disulfide coated silicon nanoparticles at 60 kV. So the goal of the experiment here is really to kind of look at kind of local chemistry in the moly disulfide layer that's on the silicon nanoparticle. With a cold FEG, we really expect to be able to get about 0.3 EV energy resolution with our microscope at 60 kV. And you can see we're getting single channel full width half maxima on these extracted energy loss spectra at this 0.3 EV dispersion. So basically a single spectrum at this condition will give us a zero loss, low loss, and core loss information up to about 300 EV. So we could probably go out to carbon K edge retaining the low loss information. If we want to have more than that at the same effective energy resolution, we need to do a dual EELS acquisition, which we'll cover in subsequent slides. So low kV, okay, short point, the low point spread function, really optimum use case for the hybrid pixel. How about higher kV? So what about 200 kV? Okay, so the point spread function deteriorates as we go above 100 kV. So we're probably going to be looking at like, say, 3 channel full width half maximum on the system that we have. Okay, so our 1,000 detector pixels for EELS is really going to end up being 300 or maybe 450 useful EELS pixels if we account for the point spread function. Okay, so just some examples, ZLPs, some zero loss peaks from the system at 200 kV at different dispersions. So just going from low dispersion down to higher dispersion, so kind of increasing the spectral magnification. You can see that the full width half maximum of our zero loss peak at our lowest dispersion, 3 EV per channel, is something like 7 EV, okay? Go down, the trend is as we'd expect. Our energy resolution increases. 0.3 EV, now we're looking at like 1.2 EV, whereas in the low kV experiment, you saw that we had like, 0.36, 0.3 EV. The take home here is that we need to use high energy dispersions to get full source energy resolution. So for example, 200 kV with a cold FEG, our system gives us around 0.5 EV in our lab. Now we need to use a dispersion of 0.1 EV or higher to get that energy resolution. So again, some real data. So this is low loss spectrum or a single EELS spectrum from Illumina at 200 kV and done at 100 millieV per channel dispersion. So a single spectrum here with zero loss, low loss, and core loss information is only going to give us up to our aluminium L edge. So at higher kV, dual EELS doubling our effective energy range, it really becomes like significantly more important than at lower kV. So I've mentioned dual EELS multiple times. Just to recap for anyone that hasn't any experience with dual EELS, what is it all about? Okay, so the enabling technologies for our dual EELS kind of acquisition. So we have 3 ultra-fast electrostatic devices in the spectrometer. So the shutter, which I've already covered, that we use for beam attenuation, and that's kind of at the front end of the spectrometer, gives us beam exposure control down to 100 nanoseconds, 0.1 microseconds. We can do then energy shift control, so up to 2000 EV with a 10 microsecond switch time, and then lateral spectrum shift control using this non-dispersive deflector. So basically you have these three components that all work as a kind of a unified system with the camera, and this is what gives us our dual EELS readout. So we essentially get a low loss spectrum, a high loss spectrum, a low loss, a high loss at very, very high speed as spectral pairs. So when should we use dual EELS? Okay, so if we consider our detector frame rates, standard camera, so the indirect detector gives you 125 microsecond kind of single frame readout in the highest mode. K3, 3000 spectra per second, so 300 microseconds, and then Stela, 9000 spectra per second, thereabouts, so close to 100 microseconds in its fastest mode. So all of these are in the region of like hundreds of microseconds or close to 100 microseconds. So what we're interested in is this switch time, like relative to these times. Okay, so this dual EELS kind of deflector or the drift tube basically is taking 10 microseconds to switch voltages. That shift is fast with respect to the camera readout time. So basically, unless we're chasing ultimate time resolution or ultra low dose, we pretty much always want to use dual EELS. And in the case of a hybrid pixel detector, dual EELS is really critical for almost all experiments, particularly if we need high energy resolution or we want the source resolution because we're constrained in our energy field of view. Okay. So this switching time is really, really important if we're doing any kind of dual EELS acquisition or spectrum image experiment. So we have this idea of fast dual EELS. So what is fast dual EELS? Essentially, it's spectral readout where we have negligible drift tube switching time from low loss to high loss. That's done live and in real time, okay? And we can do that with support for all associated applications. So spectrum imaging, we can do it that rate. In situ EELS, in situ spectrum imaging, okay? So any kind of linked technique, we want to be able to do at our full entitlement of frame rate. So just some numbers. So the solution that I just kind of went over in the diagrams, these numbers are for the Stela detector running at maximum frame rate, okay? So single frame, 110 microseconds, switching 10 microseconds, okay? If we're doing a dual EELS readout, we need to do this twice. So just multiply it by 2. That gives us a frame rate of close to 4,000 spectra per second, like a dual EELS frame rate of 4,000. So we're getting 4,000 spectral pairs per second. Dead time, okay? So the dead time is how much of that time is spent doing the drift tube switch. 10 microseconds per switch, so 8%, pretty small. Okay, so alternative solutions. So if we did the same numbers, same camera, okay, so same frame rate, single frame time is the same, but if you increase that drift tube switching time, you're going to pay a significant price, okay? So this is now a huge fraction of the total time. So our frame rate is going to come down drastically, okay? Because you're going to spend a millisecond switching the drift tube for only 200 microseconds acquiring data. So the overall frame rate is going to drop to like 800 spectra per second. And nearly all of that time is spent switching the drift tube, which is extremely unfavorable. So you'd have to be much more careful about designing pixel times in this regime than this regime. So huge speed loss, massive amount of dead time. So being able to do this fast is really quite critical to a kind of manageable spectrum imaging experiment. Okay, so that's a lot about kind of technology. Where do we go next? So now kind of onto the more fun things. So actually some samples and running the system and seeing what we can do with these features. So this is a nice case study. It's from this potassium sodium niobate sample. So this was a sample that was provided by Shelley Conroy from Imperial College London. And what is it? Okay, so essentially potassium sodium niobate is a lead-free piezoelectric, so ferroelectric ceramic with this chemical formula. So the sample that we're looking at is an epitaxially grown thin film on strontium titanate. So this is just some example data. We're going to dig into this a little later. But what's really fun with this sample is we have tons of ionization edges and different edge types across the spectrum over a wide energy loss range. So here is an example spectrum from the sample. I think this is summed over the entire area. So this is with the lowest dispersion, so 3 eV per channel. And what's really cool here is this gives you approximately a 3000 EV energy range. We've got 1024 pixels on that Stela camera, but massive dynamic range. So you can see that we have the zero loss peak and low loss. It's slightly obscured by this strontium N label, but we have zero loss peak. And then we go all the way out to niobium L, which is close to 2400 EV. And then summing lots of these counted frames, you can see that we have really nice SNR like over that whole range of that spectrum in a single kind of range there. So what do we have? Okay, so we've got K edges, oxygen and sodium at 532 and around 1000 EV. We've got L edges, potassium, titanium, strontium, niobium. We've got M edges, so strontium and niobium. So real full house of stuff going on in our spectra from this sample. So we'll start off with some spectrum imaging in a kind of conventional acquisition modality. So what do I mean by conventional? Essentially just defining our 2D array, acquiring our data in a single pass. So if we're doing fast dual EELS, we're going to get low loss and high loss. And there's a couple of different ways that we could do this. So just as a benchmark test, the first thing that I've done is use a relatively long spectrum image pixel time, so 1 millisecond. I say relatively long because that's pretty fast, but it is relatively long in terms of what the camera is capable of. So what can we do? Okay, so if we're acquiring for a longish pixel time, we can weight the exposure time towards the high loss. So this data, 200 microseconds in the low loss, 800 microseconds in the high loss. And just scanning over this, this area here that we see in green. So as I said, this is done on an F200 in our lab. Okay, so key thing here is this is an uncorrected instrument in a non-ideal room. Okay, so it's quite noisy and unstable room and no CS corrector. So not an ideal environment, but we're still getting kind of atomic resolution at this acquisition condition, which is quite fun. And then the final thing, this is 180 picoamp current data, okay? Okay, so what do we want to do? So we want to see what EEL spectra we have. So I've just got some example EEL spectra from this region here. So it's dual EELs using 3 EV per channel. Strictly, this doesn't give us that much in the way of interesting chemistry because these guys overlap heavily, but I've just done this intentionally just to show you the kind of the differences in exposure. So as you'd expect, our low loss, which has lower exposure time, just has lower signal in our ionization edges in the core loss. So the red here is an overlay of the high loss, the low loss on, yeah, this is labeled backwards, sorry. So this is actually the low loss and the the higher intensity is the high loss. Okay. So this is one thing that we can do. Basically, use this kind of dual EELS acquisition to increase SNR in the low kind of signal part of the spectrum by just having more acquisition time for the high loss. Pretty straightforward. What else can we do? So we can actually do something that's different. We can, instead of doing that, we can run the camera as fast as possible and basically just give ourselves a single frame for our low and a single frame for our high. We do that in the fastest mode. That means our pixels are now 200 microseconds instead of 1 millisecond, and it's 50-50 weighted. So low loss is 100 microseconds, high loss is 100 microseconds. Same probe current, same sample, same sampling, right? So what's different here? Essentially, if everything is basically the same, what we get is a much bigger field of view in approximately the same amount of time for the same kind of pixel resolution. So our spectrum image pixels here are 1 angstrom in both cases. We have our 4:4 mosaic subscan, so we're getting 4 times as many image pixels in the ADF in each axis as we have in our spectrum image data. So we have this kind of super resolution ADF image in basically the same amount of time. So significant win. So this is conventional data acquisition. So what other things might we want to do to change how we acquire the data? So instead of doing single passes, maybe we might want to consider doing multi-passes. So this is where all of these new kind of synergistic features come in. So next generation spectrum imaging really brings together many things. So it brings DigitalMicrograph 3.6, features of the DigiScan, features of the camera, and that's all in the Gatan eaSI framework. So that's our full kind of stack solution, and it's very tight integration between the camera, the DigiScan, everything kind of all unified in the software, giving you these like very powerful features. So the things that are particularly important for dose efficient spectrum image acquisition are listed here. Okay, so we've got hardware synchronized subpixel scanning with the DigiScan. So this is giving us sub-scanning capability at full speed of our EELS or diffraction detector. So previously this would have been limited to 100 FPS. Now this can be done at thousands of FPS. So it matches the speed of the camera, much more powerful. Big benefit here is that we can get super resolution ADF imaging with respect to the paired spectrum image data. So we can mosaic these subscan pixels, and we have more pixels in these ADF images than we do in the SI data. Next in line, we've got continuous multi-frame scanning. So there's 0 scan reset time if we want to do a multi-frame acquisition. That gives us 0 dead time if we're doing multi-frame acquisition, which is obviously a significant win, especially if those passes are very fast. Now, we might want to do drift correction. So if we can scan continuously, we really need to be able to also measure drift continuously. So no scan pause to perform drift correction, and the drift correction can be performed continuously in real time, okay? In situ. So we're doing multi-pass. Maybe we want to save all of those passes so we can record time-resolved spectrum image data sets. So this multi-pass scanning can be done in a way where all of those passes are saved separately. This is ideal for in situ, but it's also ideal for any experiment where we want to fractionate the dose or just go at high speed. And then I put this in blue because it's strongly related. Electron counting cameras. So doing all of this high speed multi-pass data acquisition, we really want to be able to do it with a high speed, high DQE detector that has 0 readout noise. So when we sum lots of frames, we don't pay a readout noise penalty. So yeah, that's basically all of the key elements for doing this kind of very, very fast dose efficient spectrum image acquisition with this technology. So just one slide that's a slight curveball just to show this in action. So this is continuous SI with live drift correction running. We've got drift correction running on the left, drift correction off on the right. And you can see basically the way that scan is running, it never stops. And I'm actually moving the stage here with the piezo. And you can see that without the drift tracking, you very quickly get blurring of the features that we have in this target region. And on the left, this 3D NAND, you can see that that drift correction is giving kind of perfect spatial correlation frame to frame. And this is really kind of the workflow that we're going to be using for this STO KNN sample. But yeah, just easy to show with this 3D NAND sample. Okay, so let's get on to our actual sample in question. So the first thing that I did was play around and try and optimize the current. So the probe current and the dwell time. So what did we do first? So decided straight away not to use 180 picoamp probe because we're scanning this area multiple times. So the idea is to fractionate the dose. So we took a guess and dropped the current by a factor of 2 to 90 picoamps. And then just start off with this benchmark pixel rate of 1 millisecond. Okay, so quite a small pixel size, 0.4 angstroms. And then sub-scanning, so our ADF image has 0.1 angstrom pixels. And under this condition, we're looking at 105 seconds per pass. Okay, so the dose per spectrum image frame here is probably something like 56,000 electrons. So this is 10x sped up from real time. And this is the experiment in action. So require the data. So we can see the first pass comes in. And then as soon as that scan, starts again, it basically just repeats and repeats and repeats. So with this this scan rate, you can see that we have kind of non-rigid artifacts in the lattices of the film and the substrate. So we have, basically we have intra-frame drift, some scan artifacts, and then if you look carefully, you can kind of see lines occasionally due to probably cold feg tip noise. And then probably a shift in this interface of a unit cell or more. So this is going to be difficult to work with. So ideally, we would want to have kind of a rigid looking lattice and kind of no warping. And that shift is also going to be painful or impossible to correct out afterwards. So, okay, so this is our first round at this. So how about the second attempt? So what do we do next? Okay, so try with the same current, run much faster. Okay, so now we're looking at 220 microsecond pixels. So high speed mode, 100 microseconds for each. Same spatial sampling and the same current. Now this is actually like post acquired data that we are like, I'm going to just show you looking through the time series after that data was acquired. And you can see over this field of view and this kind of scan density and current, you can see the STO looks okay. Maybe it's like a rigid looking lattice, so we're getting rid of that warping, but there's kind of one fundamentally terrible problem here, that the film, the KNN film there is getting really damaged quite severely on the left-hand side. So it's just like removing a massive amount of material. So the drift correction here essentially just stopped working with the default settings because it's based on a fixed reference at the beginning of that experiment. And the reference is like then completely different to what the sample looks like. So it just doesn't work towards the end of the scan. We could do some things to like kind of fix how the drift tracking works, but fundamentally this data is not good because the sample has basically got a hole in it. So it's better to just adjust the acquisition conditions and work with something else. So our third kind of acquisition strategy, what did we do? What did I do? So I decreased the probe current even more. So again, by a factor of 2, so down from 90 picoamps to 45, and then moved to a single EELS acquisition strategy. So we've gone up from 4,500 pixels per second up to 9,000. And then there's a third change here that I've basically made the spectrum image pixel slightly bigger. So we're looking at 1 angstrom SI pixels instead of 0.4 angstroms. So all of those things combined decrease the dose significantly. So we're looking at only 1,000 electrons per angstrom squared now per frame. And each frame is only going to take 4 seconds to acquire. So if you look at the ADF scan here, you can see that this is much, 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 much better. Okay, so continuously scanning, the drift correction is working very, very well at this drift rate, and the sample integrity is retained. So the lattice looks rigid, we don't have any damage. So there's probably some minor inter-frame drift, so drift between passes, but it doesn't look like we have the same warping that we had previously. So the sample is probably more stable because the current is lower, and the scan rate is like also much higher. So it's kind of like a double win here. So what's kind of fun, particularly here, the total dose of this experiment is actually what we had in the first experiment in a single pass. So much, much lower total dose and much better dose fractionation. So that's all I wanted to show regarding acquisition. So now we'll switch gears and look at the data, okay? So processing workflow and the results. So we might ask ourselves, 45 picoamps at 9,000 spectra per second, is that really going to be useful? Are we going to have any signal that we can work with for this energy loss range? So the signal intensity from a single pixel and a single pass is low. But remember, the counting detector has 0 readout noise, so we can sum post-acquisition without any real penalty. So what we're looking at here is basically the first ADF frame. Okay, so you can see that we have good spatial resolution, poor SNR in the ADF image, and then to the right, this is what the EELS spectrum looks like from a single pixel, 1 angstrom squared. So you can probably, if you knew that there was titanium and oxygen, you might be able to sort of say, maybe there's something in this region. However, looking out where our strontium L edge is going to sit, there's really no useful signal there at all. The first thing that we can do is try and sum spatially. So increase the size of this picker ROI from 1 angstrom squared up to 2,000 angstrom squared. And the EELS sometimes that gives us is just over 200 milliseconds. So now we have a very good quality titanium L edge, oxygen K, and we have something that starts to look useful in our strontium L region. So we can't see the full fine structural shape, but we can see that there's an ionization edge there in the right place. So we've summed spatially. What we really want to do is sum in time. So first thing that we should do is validate the live spatial alignment. So we do that in software with these in situ tools. Very, very simple. So just go to the in situ technique, and then you can just press play in the player and it will just loop through those spectrum image passes. So I've annotated with that cross just to kind of look at the lattice. Measure using the spatial alignment tool to get a drift profile, and then just go back to in situ editor, remove spatial drift, and then play through it again. So we can kind of validate the live correction and then see how it compares to a post post correction. So you can see like this is a very, very fast and simple thing to do, particularly with the ADF data, because that data is nowhere near as big in memory as the EELS or 40 STEM data. So really now the real-time drift correction just needs to keep the target region in the field of view, and then we can post refine that afterwards, which is very, very nice. In this particular case, the drift rate is minimal due to the scan speed and sample stability, but I think the refinement did do some marginal improvements there. Okay, and yeah, as I said, very, very easy to do with these inbuilt tools. So we've done the spatial alignment. What next? So, okay, so we validate the spatial correction, apply post refinement. In the context of a dose fractionation experiment, we want to check for beam damage. So we should look at the final kind of passes, and we want to validate if they have integrity or not, and then choose how many frames in time that we sum. So what I've done here is I've summed the entire time series. So all 42 spectrum image passes in this data set. So looking at the ADF first, you can see that we have a very nice SNR ADF image now. So if you look at the STO, you can see the unit cell structure like pretty clearly. Same for the KNN. And then now it looks like there's actually some different kind of interface structure here, which is pretty cool. Looking at the EELS data, okay, so first of all, let's just look at some summed data. 1500-ish angstrom squared compared to 2000 angstrom squared in the previous sum. So like order of magnitude, it's like not dissimilar to what we looked at before. But the sum time is now much longer, okay, because 42 passes. Titanium and oxygen don't look that much different to what we had before, but the strontium is now miles different. So we now have enough signal to very, very clearly resolve our L3, L2, and our L1 features on the overall edge shape. What next? Okay, so this is useful for us to look at the near edge fine structure, but we're summing over a massive, massive area. So if we wanted to do some mapping and have basically better data quality in a smaller sampling region, a nice thing to do is a denoise. So if we apply denoise using the principal component analysis tool, this really boosts the SNR on a per pixel level. So what we're looking at here, single pixels in the summed time series, and the denoise data is in the solid green. And the raw spectral data is this kind of glyph overlay plot. So you can see that we have really kind of good SNR in the denoise data, which is what you'd expect. Go ahead and do some mapping with the elemental quantification tools, and you get really nice atomic resolution results from this data, which is acquired in our uncorrected STEM in a non-optimal room. So we've got niobium, strontium, titanium, oxygen, and sodium maps over a pretty big field of view. So these are just extracted signal maps because it's single EELS and it's at 3 EV per channel dispersion. So one trade-off that we make with the large dispersion is energy resolution. So we covered that in an earlier slide, but now it kind of is easier to see with some real data. So for this particular experiment, the LNS features in the high energy loss edges are fine at 3 EV per channel dispersion because of lifetime broadening. So the LNS is spread out over a massive, massive energy loss region. The same isn't true for our lower energy signals, so titanium and potassium L edges and our oxygen K. So most of our LNS features are not very well resolved due to the point spread function at 200 kV and the fairly coarse sampling. So if we want to do nicer LNES analysis, we're going to switch to higher dispersion. So 0.3 EV per channel is actually really good for this sample. It gives us enough energy resolution to very clearly resolve the multiplet peaks in the titanium L edge. So you can see really kind of quite characteristic L nodes here for the STO in this pink spectrum. And then you can see like nice L nodes changes in the oxygen K from the two different layers, so the KNN versus the STO. But we don't have to kind of make a really big sacrifice because we have dual eels. So we can do a dual eels pair, use one to get low loss information, the other to get the high loss information that we're interested in these two edges. The dual eels allows us to do a bunch of really important things. So absolute quantification, so we can get areal densities, volumetric densities, remove compensate pleural scattering. That's really quite critical for most real world samples. And then accurately define our energy scale with a zero loss peak. We can do phase mapping with those nice oxygen fingerprints. So we can kind of go beyond just a simple elemental map, and we can get phase maps for the KNN and the STO, which is pretty nice. Okay, so the final thing that I wanted to show, so we've looked at two extremes. So we've looked at 3 EV per channel, which is our maximum energy range, and then 0.3 EV dispersion, which gives us really just 2 ionization edges. So how about if we pick something that's in between? So this data is pretty nice. So this is using the 1.5 EV per channel dispersion in a dual eels kind of modality, and same low probe current, and then pretty big field of view. Okay, so like 10, 20 nanometers squared. 6.7 seconds per pass, and this data is 100 passes. So same dose per frame as my first kind of low dose experiment. Much higher total dose because I'm doing 100 passes instead of 40. Now what's nice here is, yeah, we don't have like great energy resolution compared to the 0.3 EV per channel data, but we do have enough to do phase mapping of the oxygen. And with this 1.5 EV per channel dispersion, if we have that twice, we basically have 3000 EV energy range. So we catch all of the other ionization edges that we want for this particular sample. We have low loss, so now we can do areal density maps instead of just simple signal maps. So we've got areal density maps for niobium, strontium, titanium, sodium, and then our 2 phases of oxygen, so our STO and our KNN, and then paired with this kind of super resolution, like high SNR ADF image that we get from the subscanning and the mosaic subscan image. So that's really the last result that I wanted to show. So just in closing, we'll just have a summary of the key points. Hybrid pixel-based detectors really have a super high dynamic range compared with alternative camera technologies, which is fantastic. In spite of this, EELS acquisition at conventional probe currents can often cause saturation, either in the linearity or the counting, but this is really easily mitigated if you're using Stela in a continuum and use the fast electrostatic shutter to attenuate the beam. High-speed multipass SI at low probe current is a really ideal acquisition strategy for a hybrid pixel-based detector. Using Stela with Gatan's eaSI framework and DigitalMicrograph enables this to be done at really high speed with 0 dead time scan reset and continuous drift tracking. And this is done at near 100% collection efficiency, which really maximizes the benefits that we get from using that type of detector. What else do we have? So fast dual eels is critical for getting the most out of a hybrid pixel detector due to the limited number of detector pixels. This is especially true at high accelerating voltage where the detector point spread function is poor. And then the final point spectrum image pixel rate and dead time are more important metrics for determining SI performance than just the camera frame rate in isolation. So that's all I wanted to say about that. And I'd like to thank everybody for listening. And I guess we can open the floor for some questions if there are any.
Yeah, thanks, Liam. So I'm here to ask some questions. One question that just came in regarding the K2 camera, which I think we didn't talk about, but they're
Correct.
asking, do we have readout noise in linear mode for K2?
So yeah, all the cameras will have readout noise in linear mode. That's the whole point of counting. So counting is basically providing some noise filtering. So you're digitizing the linear signal, which allows you to throw out the linear noise.
Right. Okay.
Good question.
And then next question, in the 45 picoamp data, the spectrum had half an electron in some places. How do you get half an electron?
Yeah, so that's just basically there's some data conversion that goes on after the digitization. So there's some scaling that's done. I think it basically relates to how the gain references are applied. So you're at some point in the processing chain, you go from something which is like zeros and ones to it's basically linear maths being converted into real numbers. So there's some rescaling that has to be done for gain references to be applied to make the gain reference work properly. And that's probably where that originates from.
Okay. Could someone use this same camera for 40 STEM? And can you do 40 STEM and EELS at the same time?
So the detector works extremely well for 40 STEM, and you can do in situ 40 STEM as you can do in situ EELS spectroimaging. Strictly, you can't do 40 STEM and EELS simultaneously at the same time because the optics of the filter has to change. So basically, instead of projecting an energy loss spectrum onto the detector, the magnetic lenses all change and you're projecting a diffraction pattern. However, you can set the software up in a way where you essentially sequentially acquire EELS and 40 STEM from the same area using drift correction. So you can have spatially correlated 40 STEM and EELS. And you can do that programmatically as part of kind of a more complex experiment, or you can do it manually. So in practice, you would spend, so the fastest data I just showed you was say like 4 seconds. So you could acquire a spectrum image for 4 seconds, change the filter mode. That would take another like less than 10 seconds. And then you can acquire the second spectrum image, which would be your 40 STEM data, which you could say to spend another 4 seconds on that. So you could have the two data sets within less than a minute, which is probably the best that you would get. So near simultaneous you can do. And the advantage of doing it this way is that you're going to get it from the exact same sample region with drift correction. So much kind of more advantageous than kind of doing it on a different day on a different microscope with a different detector. Good question.
Okay. So I had a comment come in about the previous question about getting half an electron, and they say you get 2 counts per pixel at 200 kV because 1 electron triggers multiple pixels. So Interesting. I learned something new today.
Hello.
Another question that came in, do you have a microscopy center or research institute that has this setup that you could suggest? Like
Yeah,
who would have this sort of setup other than our Gatan headquarters?
so there's globally there's 3 or 4, but the center that comes to mind, we have a setup that's in Munich, TU Munich, in the lab of Mark Willinger, and it's essentially pretty much the same configuration that we have in Gatan in the US. So it's a K3 continuum with Stela on an F200. So if anybody was interested in any demos, particularly in Europe, that could be arranged there.
Okay.
Then I think there's a system at UC Boulder in the US, and then 1 or 2 systems in Japan as well.
Okay, cool. And those would have the Stela camera, I guess.
Correct. Yeah, all of those certainly have Stela. Yeah, Stela on them. Yeah.
And then, does the Stela camera work for 200 kV?
Yeah, so all of the data that I just showed you is at 200 kV with the STO KNN sample. So 200 kV is currently the maximum supported voltage. So it will run at 200 kV. Just be aware that the point spread function at 200 kV is worse than at a lower voltage like 80 or 60 kV. But it works just fine. So you get like the speed benefits, the dynamic range benefits. The main trade that you make with 200 kV is the point spread function. So you kind of you take a resolution hit at 200 kV, but all of the other specs are still strong.
Okay. And again, someone had a comment on a previous question mentioning that Northwestern also has Continuum and K3 and Stela. So Northwestern University in the Chicago area. Let's see, other questions. I have a few others here. The titanium map from the denoise data looked like it was bleeding into the KNN. Is that real?
That's real. Yeah, there is some titanium signature that's in the KNN. I'm kind of at the early stages of analyzing the data, but that's not an artifact.
Okay, and maybe a related question. Someone asked, why do we have oxygen signals in the EELS map of the potassium niobate at the beginning in vacuum?
So it's not vacuum on the left-hand side. It's a chromium like capping layer, and I think it's probably oxidized. If based on what the raw spectra look like, it's not vacuum on the left-hand side. There's actually material there.
Okay. And we're almost out of time. Maybe I'll just do one last question here. I have to pick. Let's see. So if you were not using a direct detector, then this approach of using short exposure times and summing many frames, would that still be useful?
It does, yeah. So with a traditional detector, you generally want to minimize the number of times that you read the sensor because you want to avoid having like additive readout noise. So you would need to make sure that the individual spectra are above the noise floor. So you can still do the multi-frame approach, but you want to make sure that you can't start from 0 in the same way that you can with the counting cameras. So
Right, because it's
yeah.
The counting cameras is really where you get the 0 noise, right?
Yeah,
From the
exactly.
camera. I mean,
Exactly.
you always have the shot noise from the beam itself, but okay.
Yeah.
All right. Well, it is 9 o'clock now here in California, so I guess we should probably wrap up there. But thanks again, Liam, for a great presentation and answering people's questions. And if
Thanks.
we didn't get to your question, we'll send you an answer by email.
Fantastic. Thanks for fielding the questions, Ben, and thanks everyone for attending the webinar. I guess we'll sign off. All right. Bye-bye.